Well, I'm pretty psyched today. Um, some friends in the battery industry had this waiting for me when I came and visited. Um, from the looks of it, these are 2650 a123 cells in a 13.7, excuse me, 13.2 264 watt hour pack. Good shit. I don't own any of these cells. Um, and I just pulled voltage. Looks like everybody's at 2.7. So this 8P4S pack, um, and I got two. So I don't see any I don't see any bleed resistors. I'm actually curious. This whatever this board is, I know that this is a temperature sensor. Um, we're obviously getting voltage here, so I am curious what the I'm curious what all this balance board is doing, and where this thing came from, because I actually don't know. I don't know what they were in. Um, they didn't know what they were in, and it looks like a really well built pack. Uh, these cells, I haven't taken any of them out. I may just leave it in this pack. I mean, this is a pretty usable voltage. It looks like three of these are ground and three of these are power, and then two of these are something else. I haven't really figured out what all is going on, but you can see the traces pretty well. Oh, that's not good. Anyway, you can trust me. You can probably see the traces right here. But yeah, it's good shit. Um, I feel super lucky, and I'll see what I end up powering with these packs. Thanks for watching. Right. So I forgot that my linear power supply is completely fucking destroyed. This this is really dumb. But I was watching YouTube and saw some shit about people reviving nickel cadmium cells. Not nickel cadmium, nickel metal hydride. I think it was nickel metal hydride. Wait a minute. These better be nickel metal hydride. I hope nobody uses nickel cadmium anymore. Anyway, the way they were reviving it is when you had packs with a dead short, you just pew, 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 it just short out, like just dump a bunch of voltage through here. And I guess the concept was that you had crystal buildup and internal shorts from the electrolyte electrolytes, whatever the fuck the proper word is for that. The soup, the paste, and when you put a bunch of voltage across it, you essentially would blow those out. and hopefully get some resistance and hopefully have a battery again. So I tried it on this using my linear power supply, and I blew the supply. So I actually have to repair that first. So I don't have anything awesome to get these charged up to a specific voltage. One thing I might do, I've got standard hobby chargers and shit. I mean, I guess I could just give them the balanced inputs and let it charge it, and then the board in between here will just do its thing as well. Might be interesting to see what's going on, because I have a feeling like I don't see bleed off resistors, and I assume that these little dudes, my eyes are so old and I just woke up, I can't see what these fuckers are. Let's look. I don't have autofocus on. Oh, I did this to myself. I have a script called Focus You Fuck that disables my autofocusing, because this camera always seems to focus one step out of focus. Oh, this should fix it. Alright, let's see. Auto 1. Yeah, sorry, I don't have the greatest flow here. Alright, let's see if we can get... This thing actually does pretty well usually. Come on, baby. Oh. Nope. Wow, this is just for my own edification. And look at that. That's a smart looking chip right there. Let's see what that is. There we go. Oh, it's gonna piss me off. Hang on, I got some sort of microscope chip or USB thing here. One sec. Well, this is fucked. I've never had trouble with this camera before. But today it's giving me trouble. I did actually just swap out. I have a decent gaming box, and I had absconded that for my workstation. Just, new hardware generally gets Linux on it, and then but I've been gaming a lot, and so I actually had to swap the two workstations. So I have like actually a really beefy Z800. It's amazing. I got that thing for like $500. It's got 12 cores, 96 gigs of RAM. I added to it for like $200. It's a wonderful workstation, but I just went through the process of literally releasing my really nice gaming box to become a Windows, which that's really difficult for me. And then I have a really nice workstation now. But apparently, I don't know, during the update, this little camera has UC video issues. So whatever. I don't know. I'm gonna look through whatever means I have at the sort of layout of this board, which I do think is really nice. But like I guess what I was saying earlier is I don't think that this has any bleed off resistors. You know, I think that these are all likely I don't know what the fuck you call them. My brain. Watch this. Focus, you fuck. See? My little C920 doesn't focus. Anyway, but these little dudes are potted. They're actually well protected. My hope is that that this system actually will bleed higher voltage from one string to lower voltage of another string instead of the typical balancer that is bleeding off excess voltage using resistors. And then I'm guessing that, you know, here this is the actual the protection, which they do 2 lines of these. I don't, you know, usually you see crap in parallel. I mean, here's 5 in parallel, but then another 5 in parallel, and it's just hopping across that line. And then I'm guessing like a fuse right there, or a thermal cutoff. I don't know. So I'm sure this thing is a balancer of some kind. I'm sure it assists in charging. I'm hoping I can just give it voltage, and when it reaches the right voltage, it'll cut off. But I haven't tested any of that. I don't know how any of this works. I'm not one of those dudes. And my power supply is blown. So what I may do is actually just go like the pack. I think full charge. It's like at 11 something right now. It's a little bit low. I need to actually look up the full charge. These are lithium nano, which I think is just lithium ion. I don't know why, or I don't recall why a123 called their nano cells not lithium ion, or if they're a slightly different chemistry. They could be. But yeah, so there's the pack voltage, and it was 2.7 on each string. Does that even add up? 2.7 times 4. Yeah. 2.7 times 4. Yeah, that adds up. So, yeah, I think these are in good shape, but I think the pack is low. I'm guessing I don't know if these are weird chemistry. All right, let's do some math here. 13.7. Oops. 13.74. Dick. They put 3. Sorry, I do math in a terminal. And it doesn't always give me the remainders. Yeah, man, 3.3. So these are likely lithium iron phosphate cells with a nominal 3.3 volt voltage. So yeah, I'm gonna have to look it up. I think that's what I'm gonna do next. And then like I said, my bench power supply is gone. I need to fix it. I likely know I blew the linear, the actual, God, my brain is not working. It's not a FET. You know what I'm trying to say. I blew the main piece. It's just giving out its highest voltage. So anyway, I'll get that thing fixed. But in the meantime, I may get a smaller supply because I've needed another, and that one is quite large. It's like a 30 volt, 30 amp thing I was using for electroplating and some other shit. So I'm gonna pick up a smaller bench supply, maybe try to clean my station, and then and maybe by then I can actually get a better view, start seeing what all this shit is. Like, you know, this looks like a decent little management chip of some kind. So anyway, that's it. I'm droning on. There's really nothing more to say. Other than I mean, maybe these will go in a fucking car. Maybe I'll put it in my Lotus. That thing is always dead. So cool. Thank you. Goodbye. All right, I can't help myself. These all have the same. They've all got the same part number, which is FS 300-475-306. See if these are thrown away for a reason. Yes, RC people. Yeah. Alright, so let's see what the RC people say first. That could be a treat. 2500 milliamp hour. That's what? That's not real good. Is he actually talking about the same shit here? Yeah, shut off is 2.5. That's what I would have guessed. Even lower. You can probably drag these down to 2. Here we go. Let's see if this is what we got. Oh, you bastard. a123 batteries. This looks like one of those clickbait sites. Oh, I hate the internet. That ain't it. That looks like it. Here we go. 3.3 volt, 120 amp, 396 watt hours, I assume. 70 continuous, 120. So, I mean, but like, uh 8 in parallel. I mean, this thing should be able to provide a lot, but this connector, I can only imagine it's rated for tens, many tens of amps, and then times 3 connections. So I don't know, you might safely be able to pull 60 amps from this thing or something like that. I mean, still not bad, because again, this connector's got 3 parallel connections for ground and for plus, but I'm too old to be able to see these dudes, and I don't have the magnifying glass. My setup here is just in disarray. What else can we find here, though? I don't think I can do math to figure out what 396 watt hours is in milliamp hours, which is a term I can understand better. Derp. Also, these charge up to 3.65 and then settle down to 3.3, which is what I'm used to. There's a cylindrical cells. Yeah, okay. Yeah, see, these are good measurements for not me. Yeah, 2.5 amp hour. Yep. Fast charge method to 80%. What's SOC? Then constant current to 3.6. Oh, 4C. I was reading that as voltage. Yeah, so this is actually exactly what I would have guessed. So they're saying you can charge these at 4C. So would that be 10 amps to 3.6 volts? Constant current. That's interesting. 100% depth of discharge greater than 1,000 cycles. So that was always kind of, I guess, the claim to fame, at least early on with a123 cells. I mean, I sure was a big fan. I mean, I was definitely one of those people that was, you know, harvesting these cells from DeWalt tools. They weren't the 26 650s, but the 16 650s. And like, for instance, I still to this day I have a 10-year-old pack that is also a a123 systems DeWalt pack with lithium nano, which I think it basically is their lithium iron phosphate mix. So, pretty much you're not going to get quite the density, and in fact, these don't have nearly the milliamp hours that I suspected they would have, but they do have incredible discharge rate. So, for a really high-powered application, these would be really good and safe, because you're not going to ever catch fire. These will not catch fire. You can poke a hole through them. You can mistreat them, and they're not going to catch fire. And as far as I know, the basic rule is you can go down to 2 volts. Really, 2.5 is a really safe cutoff. But you can go down to 2 volts, and then you charge up to 3.6, and then you stop, and the cell will settle around 3.3 volts. So I am a little surprised that the capacity of these is so low. I don't know when they were released. Minimum cell capacity is 2.4 or 2400 milliamp hours. Nominal is 2.5. So they could actually perform a little better, and it also depends on how far down you are willing to bring them. What else is in here? I'm just going through this. Anyway, you can tell I'm really excited. I'm really excited. Um, FS300. I still don't see the fucking part number, so I want to. Oh, nanophosphate lithium ion. Here we go. Let's look at this. Da 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 da. 2008. These could be quite old. And I don't know what happened at a123. Like I said, I was a big fan, and then as far as I know, we had sort of funded them. A lot of our taxes. They did good, but then I think they went belly up, and I was a big fan of their. I wanted to get some of their 20 amp hour packs. I have some other 20 amp hour packs by a company I'd never heard of that is an American company, which I plan on doing. That's probably going to run my rover, and those also are like a lithium iron phosphate type cell. So again, way less dangerous when you fuck up. You need to be careful, especially you start fucking with cells that these can push 120 amps and 70 amps continuous per cell. We have these in 8P. I mean, so maybe I'll build a jump box out of these. I've built jump boxes out of headway cells, which are much bigger. I forget what size mine are, but they're basically 15 amp hour cells, also lithium iron phosphate, which is what kind of disturbs me a little bit with these little baby jump packs that people are making and selling, is that they're all lithium ion. Some of them are prismatic packs too, which anybody that's been doing RC for the last 10 years knows those packs are potentially really dangerous. So it surprises the hell out of me that people are building jump packs, things to start vehicles out of lithium ion. You're so dependent on good battery management for those. Whereas my headway cells, I have 4 of them in parallel, and I have a battery management system on them for charging. But for jumping the car, I have them hooked up directly. I'm not worried about over discharging them. In fact, I set out to mistreat that pack. It's been working for 5 years now. But I guess my point is, yeah, if you're doing anything high powered, the lithium iron phosphate is probably the safer bet. But what do I know? And I'm happy to show some of the other batteries that I've got. A lot of these are just old projects or future projects. I actually probably need to go maintain the 20 amp hour cells that I have. They're probably sitting there discharging. So from the looks of it, these can do 7,000 cycles. So if you're nice to them, they will last essentially longer than you want them to last. That's what their nanophosphate delivers, and I'm pretty sure that's Well, I knew from the voltage that's what these were, but what's the... I thought they actually said it too. Alright, what else in here? They're going to give us actual packages. I thought this was the one that gave us... Let's look at their cylindrical cells. So yeah, now a123, as far as I know, is... I can't remember who bought them. I don't think we're manufacturing them in the US anymore, though. Handling cells, short circuits, arc flashes. This is all good shit. Let's read about this. Yep. An arc flash caused by a short circuit involving both high voltage and high current emits extremely high intensity visible and ultraviolet light. Kind of like our sun. A burns yeah, dangerous levels of current. They're not talking about explosions here. Yep. Yeah. Where's the voltages and capacity? Like that. Mechanical connection. I did also peel. I peeled back the sticker on these dudes. I peeled this stuff back, and it's just a decent what do they call it? You know, it's a welded run of what you'd expect. And then this side they had just a little PCB that ran across here and was checking temperature on each set of cells. So I don't really have a way of knowing if any of the cells are bad in here. But the way this pack sits, I don't really see a reason to rip it apart. I've got a thermal camera, so when I do some discharge cycles, I can put the camera on it, and it should be able to pick out hopefully any cells that aren't happy during either the charge cycle or the discharge cycle. But other than that, the chemistry of these is such that I'm not super freaked out about not knowing the true state of the pack. Plus, a123 cells, as far as I know, the quality is good enough that yeah, it's just less of an issue. It's not like you don't know what you're getting. And yeah, these are all laser welded, which I can't do a better job than that. So venting, insulation, these are a little close for my taste. These are packed in there pretty good. The 26 650s are probably going to be a little more forgiving in terms of heat and crap like that. And I don't think I'm going to be pulling enough current on these things to really upset them. But that pack is pretty tight. 10 to 50C. Not that great in the cold. I think lithium ion will work down to a colder temperature. All right, you gonna tell me about your actual offerings here? State of charge, energy throughput. So, what? What is this telling me? Perhaps if I read the text. When monitoring cell behavior, in fact, histograms should be stored. Current voltage, state of charge, energy throughput. Dude. I mean, that's the thing. Like, I love the documents. It could very well be the reason there seems to be a fair amount of sophistication on this balance board. You know, maybe they're going by the book. Whatever these came out of, these probably came from UVA. All right. When to balance. See, they're even kind of saying, I mean, look, you can't always balance. It, which is funny because oh shit, I'm not even showing the. Yeah, so you know, you want to balance ideally, and you want to, you know, always balance no matter how hard you're cycling up or down, but it's not always practical. That's the approach I took with my balance pack. You know, given the chemistry, like I know roughly what that pack is allowed to do, right? And I know what it's capable of delivering um, in terms of current. So, I mean, you can pretty much know when you're about to do something bad. And if you really do something bad with lithium iron phosphate, you potentially can ruin that cell. But you're not it's not nearly as dangerous as with lithium ion, where especially during charge cycles, if something goes over voltage, you begin to destroy that cell, and it can actually short. It can actually just, well, we've all seen scooters explode. Yeah, and then yeah, and so like for people that are making battery banks, like I actually am, I'm working on making sorry, I got a bug here. Fucking stink bugs around here. If you're making battery banks, you definitely need to be aware of this sort of thing. But you you need to balance your packs appropriately. But if your state of charge, if you know you're not charging right up to the limit. Like, if it's lithium ion and you're charging, your entire bank up to 4.2 volts per cell, like that's, if you're out of balance and you don't have a balancing mechanism in place, then you're going to be at that point of danger every time you charge the pack, right? But like right now, these are these cells, which again, these aren't lithium ion, but being that they're each at 2.7 volts, like right now, I know it's safe to pull voltage, and I know I could charge this too, even if I didn't have this balance pack on here. And monitoring each string, isn't necessary to a degree, as long as you're, not pushing the upper and the lower limits all the time, and you're not pulling currents that could sag voltage, down beyond where it's supposed to be at any time. So like this technology is more forgiving, but I think that well, for instance, my large battery bank that I'm building for my whole home backup, like you don't have to freak out and figure out some huge battery management system. You just have to work within what are some safe values. And of course, you do, like, I'll probably just passively monitor, and then my balance mechanism will be, I'll top off packs that are low. I'll just maintain it every once in a while, but my charger is not going to charge it all the way up to the highest level, and I'm not going to discharge it for the full depth of discharge for the cells. So that's going to turn what will be like a 9 kilowatt hour pack, 9 kilowatt hour pack, into something that has less usable capacity, but then I'll get to forgo any of the management system on it, and I'll just passively monitor each cell. So but yeah, so it's good. Again, with this technology, they're essentially conceding that, even with a high powered electric vehicle, you can be reasonable. Yeah, and if you're being nice, so you're pulling 2C, or what is that, 1/2 C, then you can just monitor the pack. Which is interesting, measuring batteries under load. Trying to, I've seen this on other packs, like oh yeah, let me just grab one. Oh shit. So yeah, like these guys, these ego packs. I'm sure everybody's seen these. These are really high voltage. I'm pretty sure these are 1P. I don't know how many are in series, but these are lithium ion. And of course, this thing has a battery management system. But even with that, if you're pushing the discharge pretty hard on these cells, how do you predict your low voltage, right? So your cutoff voltage, as soon as you let off the trigger of your weed whacker, or whatever the hell it is that you're using. Like lithium ion, even under load, if you're not going nuts, will maintain a very high voltage in relation to its cutoff, or its fully charged voltage. In other words, there's not a ton of sag, even under load. It will sag under load, but that voltage, if you measure it under load, doesn't necessarily tell you the state of charge of a pack. So, what a123 is essentially saying right here is that if you're running a half a C, and you know that the state of charge is greater than 90% or less than 30%, then then you're pretty much gonna be close to understanding what the actual state of charge is. In other words, if you pull big current, you're gonna hit that 30%. You're gonna sag the voltage enough where it's gonna appear as though the pack is already spent. Versus if you're pulling a very light current and you're measuring the state of charge through voltage, that's the only, that's the basic method for knowing the state of charge, right? You lower currents mean you can rely on that voltage measurement more. And of course, no current would be the best method, because then you know that the battery pack is in a given state, right? So I guess my point is, these packs which Ego makes, which are probably pulling several amps while they're under load. Well, Ego's going to be attempting to figure out what the state of charge is, but it's going to be under load. And one of the things I've noticed, which I think these packs are well engineered. I know people have made fun of them because they're big and kind of idiotic. They have this phase changing material in them, which I was really glad Abe actually tore that shit apart. I've seen the phase changing material, but I didn't actually tear it apart. But what I was gonna say, one of the tricks that I think I've seen Ego do, which leads me to believe that they not only put a lot of thought in the engineering of this pack, which I believe they did, because they, even the shape of this thing, the cells are mounted in such a way that they blow air up through here and cool the pack. The air exits here, so you have a nice cooling effect on all the cells, which is super important while it's being charged. They have the phase changing material, which helps allegedly while being discharged hard to keep the temperature at a steady state, because in all likelihood you're going to run out of charge before you fully change the phase of that material. And so your temperature rise is going to go up, and then it's going to sit, because you can't go beyond whatever the value is that the material is changing phase at. It's going to be absorbing heat and maintaining a level value until eventually everything has changed state in terms of that materials phase, and it will ramp up in temperature. But the goal is the pack will be dead before that happens. So they've they engineered in that piece. They engineered in the cooling. They potted the hell out of the system that monitors everything. So you can this pack is in pretty good shape in terms of the protection of the board and everything. But then when you're running your weed eater or your blower, you can actually, every once in a while, you'll hear it drop. It'll be like running full tilt, and then you'll hear it go, and it'll drop in RPMs just a little bit, and then it ramps back up. And it's doing that on maybe like a 5-second cycle. And I think the reason is because Ego is attempting to estimate the true depth of discharge under load by removing some of the load before taking the measurement. They can see sort of the delta of how quickly the pack is recovering in voltage, and so they probably have a profile that they use to basically better estimate depth of discharge in the pack using that lesser load delta. I hope that makes sense. So under full load, you would expect the voltage to sag. Under a slightly less load, you would expect the voltage to creep up a little bit. Just a little. It's going to recover just a little. Just like if you removed load completely, it would recover to whatever the current state of charge is. So what Ego, I think, does is every couple seconds, they reduce the load on the pack. They measure how much the pack was able to recover in terms of voltage, and then they basically have a lookup table of a profile for this pack that helps them determine the state of charge, but all while under load. And then obviously, if you let go of the trigger, they can get a good value. They can get a good read on where it is. But again, it's such a hard problem with lithium ion because the voltage really doesn't sag a lot. And then when it's finally done, it goes like that. And when the cells are done discharging, you have to very quickly cut it off. But again, if you're under load, you may reach that voltage sooner, and it may not actually be fully discharged. Anyway, I hope all that makes sense, but the point is, it's hard. It's hard to measure stuff under load and determine the state of charge. And I'm guessing that, or I gather that this statement right here is basically saying, yeah, because up here they said, especially with this chemistry, which is more forgiving than lithium ion, it is less important to worry about the balancing. If you're using the pack safely within a known upper and lower range that isn't the complete, the total upper and lower range. If you're 90% of upper and 30% of lower, then fuck it, you don't really have to balance the pack. You're gonna be safe, especially if your current is so low that you can reliably determine the state of charge. That's what I believe this sentence to mean. So short circuit shit. They're saying don't short circuit. Yeah, individual cell fuses. So this is like what Tesla does. This is what a lot of the battery wall builders do. This is what I'm going to do for my lithium ion pack. Basically, put small wires on every cell. Which this pack in front of me does not have. These are pretty beefy laser welded strings running into here. So, but they are monitoring voltage of each one. So, but there are no fuses in the parallel part. At least not that I saw. I didn't pull off both sides. Let's fucking look. Now I'm all curious. Also, I'm just really, really blabbing here. So we pulled off the little temperature monitor wire. It's no big deal. So here you can see just the laser welded this stuff. No fuses. You got some gunk here for the what I presume is a temperature sensor. So I would guess the other side is going to look just like this. And I'm guessing that this pack, yeah, it looks just like it. Same thing on the other side. But I'm guessing this pack is rated, somewhere between 30 and 60 amps. Little quality control purple marks from humans right there. A human touched this. What else we got on here? ABS. Nothing else telling. Nice hardware. Good little lock, nylon nut lock bolts. Shit ain't gonna come undone. Yeah, so I mean this pack is can probably safely deliver I really would like to know what these chips are. And I really would like to know if indeed this is dumping voltage to the lower voltage packs. Like this I think this looks like a way more efficient balancer than what you typically see, which is just bleed resistors. So yeah, I'm excited. I figure I don't know what these cells are worth. A couple bucks a piece. And oop, I did break that connector. That's a bummer. That's a bummer. All right, so I don't know, I may glue that back. That's interesting. That's a bummer. All right, are they ever going to give us the other capacities here? That's all I wanted to see was what the packages were. Derp, derp, derp. How to properly fuse things. Yeah, see. Yeah, so lithium phosphate's weird because you actually charge it up to maybe even 3.6 volts, and then it settles down to 3. And over the temperature, these don't vary that much in terms of resting voltage. I think this is all resting voltage under a really, really small discharge. And that it looks like this was for this style cell, the 26650s. Yeah, so one method of determining the state of charge uses only voltage. The BMS takes reading of the, what's OCV? What's OCV? Oh, look, using lookup tables based on the chart in figure 12. Yeah, so still, you get good delivery, and then boom. So under load, that can be hard. Okay, and then this is open circuit voltage. So we're oh man. Anyway, we're at 2.7. Wait, what's going on here? Yeah. See, it's a tricky chemistry. So they're saying here 3.3 volts could mean it's 66% or 43%. Depends whether you just discharged it or just charged it. And this is open circuit voltage. So this is just at rest. This is not being charged and not being discharged. I'm at 2.7. It's not on the chart. Another method uses only current and time. So here you're going to estimate milliamps with a known starting point. So again, like, you know, applying this to lithium ion, like, same problem. So, you know, probably the Go people are actually they could be doing both. But I know that they remove a little bit of load. to help with their calculations to try to make this pack safe. Like you can hear it. You're like, oh shit, my weed eater's dying. But then it steps back up a little bit and is fine. And I think it's because they're taking a measurement in between. They're taking measurements every 10 seconds to try to figure out the state of charge. So it ain't this shit that nobody wants to cause fires. Circuit voltage reading taken after current is taken out of the battery will result in another. The difference between these two voltages varies over state of charge and even temperature. So here we've got the hysteresis, which again, pretty close, and especially if you're working within a well-known state. So I'm guessing these are fully discharged at 2.7, which is probably the cutoff of this balance board. But there is some uncertainty, and you of course have to know if you're using the battery or if you're charging the battery. So let's see if there's anything else. I'm talking 0.02 volts of uncertainty, which depending on the system, but for me it's not going to matter. Yeah, self-discharge test. See, you get lots of info here. This is what buying cells of known origin gets you. A crush test, drop test, shock test, immersion. Do they actually give us stuff for this? Cell incoming inspection, material handling, storage, cell welding. Look at that. They give you vendor-specific welders with their specific welder heads, things like that. Did they give us any values? Neg 40 to 60C. Anything other than that is a no-go. Oh, here we go. So here's the actual specs on these actual cells from the horse's mouth. So 2500 milliamp hours, 70 amps. So those other people were liars. See, pulse at 120, 210 watt, 10 seconds, at 10 seconds. That's another good measurement to have. 1.5 C, so 2.5 amps times 1.5 to 3.6 volts. That's how you want to charge them. But look how fast you can charge them, which now there's like 10 C cells and things like that, but oh, and a float charge of 3.5. Aha, see? I thought these went down to 2 volts. So to get to full capacity, 2 volts, man. So I mean, you've got quite a range. So these are mid 2.7 volts. These aren't completely dead. but they're probably darn near it. But they're probably in good shape. And I don't know what their M1B chemistry is, but obviously it's a lithium iron phosphate. Yep, there's the package. That's our cell. The vent is actually on the bottom. That's good to know. And then these are the 18650s, which quite a bit less capacity and quite a bit less current. So these are really high current cells. Oh, 4C to 3.5. What did these do? 4C to 3.5. Okay. Fucking neat. These are probably like what I harvested out of my DeWalt batteries, which I still have some of those. And I have an 18-volt pack that is my go-to pack for my DeWalt shit. The thing's 10 years old, and it works, you know. So batteries started really having the ability not to suck like 10 years ago. And I remember when a123 came out, and I was so excited. And then there, I've seen YouTubes of their prismatic cells, the 20 amp hour cells, just being short circuited until they're discharged completely. And the performance of those things seems great. And I wish I had a stack of those, but I don't. I do have another stack of 20 amp hour prismatic cells, though, of a similar chemistry, just a different vendor. And I'm going to be building a pack out of those for one of my robots. All right, I think we're done here. So that was not very useful. We did discover exactly what these are, though, and how to charge them. I guess the next step will be if I actually just charge through, I know I have voltage here. If I charge through this BMS, we'll just see if it behaves. So I'm just going to give it 1.5 C or whatever. I'll just limit it to I don't know, 3 amps or something, or maybe 5 amps, and yeah, just throw it on the charger and see. I mean, honestly, I don't even need my linear power supply. I can probably just find something that will go, up to what's the math? 3.6 times yeah, I can't math right now. 14.4 volts. So as long as I can do more than that, even if I don't have a decent bench supply or whatever, because I blew mine up, it'll sag to whatever the pack voltage is, and then the BMS should protect it from overcharging it. And then what's really cool about these, I didn't realize that you can float them at 3.5 volts, which I find really interesting. I was under the impression that for lithium phosphate, you wanted to charge up to, typically, and again, this is other people's chemistry that I've worked with, but typically, like, 3.6, 3.65 is your typical cutoff voltage for most BMSs. for lithium iron phosphate, or LIFE PO is the other acronym or whatever. But as soon as that happens, I've always thought that you generally wanted to remove voltage and let these sit, and they should come back down to their 3.3 volts. But these cells specify that they can float at 3.5 volts. So what does that mean? Because, if you float a cell, like I thought typically a float was used, well, I mean, obviously to top off, to keep the cell fully charged so that its internal resistance isn't discharging the pack. Like, to keep it on the ready, I believe is where you would, why you would ever leave it on a float. But like typically there's, my understanding is there's usually 5 different states of charge. Like when you talk about lead acid batteries, you can obviously float them, right? But you can also, they need to be balanced too. Lead acid needs to be balanced too, and they don't have any kind of management. So I forget what the 5th state is, but you charge higher than the cells want, and the cells that are overcharged just dissipate that energy, but the cells that are undercharged will be brought up within that pack. So that's why that is pretty much what your alternator does every day. Is it just it's your battery in your car is spending time dissipating energy as well if it's at full charge. And that keeps that pack in balance. And of course, lead acid is just way more forgiving. But what I don't know is if you float these, if strings of cells that are low will come up, if they'll continue to charge, while others that are fully charged at that 3.5 volt float value will dissipate. So in other words, like a poor man's charger would be very low current at 3.5 volts. Will that bring strings of cells up very, very slowly? Either way, doesn't fucking matter. I have a management system on this that I'm guessing is intact, because I don't see anything wrong with these packs. I don't really understand why they got recycled. So I will run off and figure out how to cycle these, and then I'll probably get them charged and look at the behavior of this shit, see if it cuts off, at what value it cuts off, and then see maybe where the strings end up sitting, where everybody sits. I'll get some thermal cameras on it. Not that I doubt I'm gonna be charging or discharging at this point at a rate that will get any heat out of any of these cells. But we'll see if there's any, maybe there's a bad cell in here, and that was part of the problem. But right now, I don't see any evidence of that, just based on each of the strings voltage. It all appears fine. So yeah, so charge them, discharge them, do a couple cycles. We got 8P, so 2500 times 8. I use DC. It's a math thing. So that's 20. Yeah, that's 20 amp hours. So this is a 20 amp hour pack at 13.7 or 13.2 volts. I don't think I can put these in a vehicle. I don't think they're going to be happy with that. I think for lithium iron phosphate, I'd want 5 in series. you know, because then you're within the range of what a vehicle's electrical system is typically going to do. In fact, you're probably in a danger zone for some vehicles. So I don't know. I've run around with I'd say depending on the vehicle, but I don't know. These are probably going to have to go. Ugh. I'm going to have to design something for these to be used in, because holy shit, what a great find. Anyway, if anybody's interested or still here and wants to see any of the other weird batteries that I've got some prismatic cells that are pretty dangerous and big. They're 20 amp hours a piece, I think. I've got headway cells that I built into just a jump box with a small battery management system for charging. Real basic stuff, but it's made my life really convenient because I have a lot of cars, and jumping cars, I fucking hate the jump boxes. So I built my own. I thought of building a new one out of those prismatic cells as well, because they perform really well. But I have a 60 volt 2P pack of those prismatic cells, and I actually have a robot or a rover that is like a 36 volt system. So I may end up doing a jump box out of those, as well as creating a few packs for the rover. But I may just end up using all the packs for the rover. It really depends on how successful that build is, which has been ongoing, and I haven't ever finished it. So none of this really happens. But if you want to see those packs, I can drag them out, and we can try to look up the specs on them and figure out how dangerous they are, things of that nature. Anyway, I think that's enough. I'll see you guys. Okay, so god damn it. I'm not gonna go editing. Here is the battery management controller with power pump. It looks like it's a 78PL116. Support for LCD and electronic paper displays. That's kind of fucking cool. 11 amp, 26 amp, or 110 amp operating current. So I know at least we can pull 11 amps. Probably the little dudes on the output in parallel. There's 5 and then 5, which I don't really get. In parallel, well, 5 in parallel, but 10 or 2 sets of those in series, which I don't really get. And then we're doing 4 series cells. So this is what that chip is. I just want to see if there's anything else cool. The LCD support seems really cool. I didn't see any other connectors. And now, I mean, obviously I'm just blabbing even more. But I don't see any. Oh, come on. Yeah. Sorry, my flow here sucks. I don't see any additional sensors. If LCD can work over 2-pin, maybe maybe it's coming out of here. But yeah, this little dude has LCD capabilities apparently, or e-paper. So that's quite interesting. Here I'm reviewing my own video, so I'm just pulling up that shit. And I'm getting pack voltage out of the connector. So right now, at least, it hasn't detected any cells. Looks like it measures impedance. And here we go. Power pump technology transfers charge efficiently from cell to cell during all operating conditions. Which basically, that means this little dude doesn't just bleed off. It's actually doing what I said, which is transferring high voltage to a lower voltage, which is why, you know, we've got all these dudes instead of some kind of bank of of resistors that bleed off voltage. So in essence, this is an efficient system. 18-bit delta sigma column counter. So this is using the second method that a123 described, where you count columns. So it's actually measuring charge flow for gas gauging. That's good. And temperature, yeah. Pack current and individual cell voltage. 400 microamps, 185 microamps standby, less than 85 microamps ship, and 1 microamp under voltage. That's good, because when your pack is under voltage, obviously you don't want to be pulling a lot of charge to power your your battery, your BMS, right? So this thing is smart enough to know that it shouldn't be doing that and just pulls less than a microamp. So that's good shit. Up to 3 power MOSFETs and 1 secondary safety output fuse. And then all the voltages are programmable, so you could use it with different, varying chemistries of different manufacturers, is what that means. That's what that means to me, anyway. E-bike, uninterruptible power supplies, handheld tools. Maybe we can rig this up to work. Like one of the things on my list is to just have a external pack for running power tools. This might be good for running. I guess it's going to be a little bit lower voltage, but I have some 12 volt Milwaukee tools that this would probably run all day long. Make the tool a little lighter. Just set the pack under there. In fact, I'm going to go tear apart our car probably very shortly to replace some rod bearings. So, laying the pack on the ground and just, it's not like I run out of battery with those tools anyway, but whatever. It's something you could do. Power pump technology transfers charge between cells. So transfers charge is the operative word here, because again, you lose so much efficiency while charging, and also the speed at which you can charge. If you're burning off power, which is what any typical hobby charger does, it monitors each pack or each cell, and then typically will burn off voltage. And in fact, I never liked that setup. I always preferred chargers that actually hooked up to the balance port and only balance the cells, because typically you'd be limited to 3 amps because of the tiny wires, but you could put 3 amps in each individual string. Whereas if you're hitting the pack and dumping voltage in there and just monitoring here and trying to burn off voltage on a given pack, like depending on the state of the pack, it may be a way more or less efficient charge over time, because at some point, if you really want to balance that pack, you're going to have to bleed off the highest cell until the other cells come up. So this system gets around that by transferring higher voltages of one string to the lower voltage of another string. So that means you can just charge it through this port, and you're going to get basically a lot more potential current in the transfer than you would versus the current that you get in a bleed off. So probably overall way more efficient design, and not typical, at least in what I normally run across. In fact, I've got other balancers. I've got one to build out my Rover pack, which is that 36 volt pack. Similar chemistry. I think it's a 12p. I might have even done a 15p. I can't remember, or 15 series balancer. But again, it does the same thing. It bleeds into heat during the balancing operation. So, and most hobby chargers now hook into the pack voltage, and they either bleed internally or using an external board, they bleed. So anyway, this doesn't do that. This transfers, which actually means it might also be good for things like super caps. But it kind of depends on how beefy you build the circuit that does the transferring. Yeah, so highly efficient charge transfer circuitry nearly eliminates energy loss while providing true real-time balance between cells, resulting in longer runtime, improved cycle life. The reason you'll get longer runtime is because low voltage cells get brought up with very little loss, and so the overall pack cutoff is always going to be whatever string reaches low voltage first. So if your pack is more balanced, then yeah, you're going to get more runtime. And then of course, the efficiency at which you can transfer that energy is a huge part of it. So anyway, yeah, this one is constantly doing that. Voltage balance temp, voltage balance temp. So these are all the inputs. What else we got here? So it looks like you have to flash it if you want to change the configurable values. So like if I wanted to adapt this for, I have some 3000 farad super caps, and it looks like at least for 4 of these, they had some notes if you want to do more than 4. But if I just want to copy, since I'm not good at designing, if I just want to copy sort of the design of this circuit or use one of their reference circuits, then I'd flash it for what my voltage values are. And then you could actually build, it looks like at least a 110 amp system that would safely be able to deal probably with supercapacitors too. And yeah, so where's the display bullshit? We got the column counter. Got some GPIO. Might be interesting to see what 2 pins are wired up. What 2 pins are wired up on the on this dude right here, which to pull this apart is going to be kind of a bitch, because I'll have to desolder it. Which isn't, a huge deal, but but I may not get there. If these are completely useful as they sit, I don't see any reason to change it. But yeah, it's good to have a nicely done reference design with this chip if it ends up being something that I might want to use later. Because I actually always I don't know how to find, like, I know what I want, but I don't know how to find what I want. Like, I've always wanted to design my own BMS. But this is what I want. I want to transfer current. I don't or transfer voltage. I don't want to bleed voltage. And most of the stuff I see is for bleeding. So anyway, this is good for me because maybe I can hack my way into something cooler. Cool. Watch Dogs. Where's the LCD bullshit? Derp, 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 derp. Okay, so here's a bunch of these in series. Oh, and then a master gateway. Wait. Oh, okay. 76PL102. So one of these should be somewhere, or two of those should be somewhere, right? 1, 2, 3, 4. Oh, with 4 you don't need it. But then if you want to do additionals, you can add this little dude, and then this same chip will deal with a more, looks like up to a 12 series pack. So that's really rad. So we're just using it with 4, so we don't have any of these. So that's kind of badass. I like it. 3 to 16 series cells, and yep. So what can we get from the display? What can we integrate into this thing or not? Because I usually never successfully do anything. And why are these MOSFETs, I'm assuming, why are there 2 sets? I don't, I'm not the sharpest tack, but why would you design 2 sets of these? Because to me it looks like here and then here. Why would you have 2 sets of these in series? And is that what's actually going on? I guess I could potentially figure that out, but it looks like, oh, unless these are all in parallel, maybe no, I don't see how they could be. Yeah, they're not. Yeah, so why would you do this? Somebody smarter than me tell me. And chances are you didn't make it this far, so you're not going to tell me. But if anybody knows, I'd love to know. I don't understand. All right. So let's see what else is in here. Okay, so you can do segmented displays, it looks like, or an LED. So at the very least, maybe I'll wire up some LEDs or something. Yeah, 5-segment display from the looks of it. What else? Is there anything else interesting? The range on this chip is higher than the range for the batteries in terms of temperature. 400 microamps at 3.6 volts per cell. V1, V2 is okay, whatever. Extreme cell under voltage shutdown current. Any cell less than 2.7 volts. And any kind of looks like, I wonder if they didn't really program these. Because again, you can push these cells down to 2 volts. But they may have left headroom. Five nanovolts resolution. I mean, at 18-bit, I guess I'm not surprised. NVH, is that nanovolts? I don't know. Okay, plus or minus 2C. The external temperature. Doop, 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 doop. Anything else look hackable? I mean, just the LEDs maybe, or LCDs, but I think they were reaching a little, saying it supports paper displays. I was excited and thought this thing might have a lot more brains in it. But either way, this looks like a good, you know, good shit from Texas Instruments. Auxiliary FET control. Battery cell under voltage, pack over under voltage, charge, discharge over current protection, short circuit protection. So we can short these pins. External MOSFET control inputs. That's interesting. 4 external temperature inputs, which it looks like we have all 4 on there. A watchdog, a brownout detection. Yeah. Abnormalities, rate of change. Looks like yeah, impedance rise due to cell or weld strap fault. So if any of the cells were shorted and or open, or you know, the impedance is going to change across the ones that are in parallel. So again, I'm not going to rip this pack apart because I think it's probably in good shape, and from the looks of it, this little chip would have detected something like that. So once I cycle these, we'll see if they do anything weird. I don't know what any of these specifications are. Patented power pump technology. Well, if it's fucking patented, I mean, that's bullshit, because whatever. Fuck patents. 0-volt charging with separate MOSFET control. I wonder, I mean, Pre-charging and 0 volt charging. Whatever. I mean, nothing else, you can bring the voltage up on a given cell. In fact, that's how I repaired most of my DeWalt batteries. They were all fine. Just one cell was a little bit low, so the device didn't let it charge. So you just give it a little bit, and that's good to go. 3 to 5 segment static liquid crystal display. 3 to 5 segment electronic paper display. So whatever. We could do LEDs. We could do LEDs to get the oh, here we go. So on this SMBus, this might be really fun. Lifetime delivered amp hours. Last discharge average. Lifetime maximum power. So we can profile the history of these particular cells if we can bust into that SMBus. So that actually might be really a good thing to do. And I can report back to Central Battery, who gave me these, what the story is. I don't think that's funny. Max and min temperature, max min pack voltage, max min cell voltage. So man, that's really cool. So it's got lifetime logging. Fuck yeah, that's really cool. I'm really gonna try to go for that. Once per second. It's doing its calculations once per second. Oh, interesting. So I wonder, actually, and I'll have to confirm this. God, I'm staring into this really bright light. I can't see. So they mentioned the different modes, which I assume some of these are automatic, but I do wonder if I've been wondering what these dips do. Like for instance, you might be able to put this into shipping mode, in which case you're not getting, you're getting less than a microamp current draw. So figuring out what these do, figuring out where the SMBus is, I think will be super fucking cool. Man, yeah, it's like Christmas. State active, fully active, normal operation as determined by firmware. Firmware directed to the following operating modes. Standby, fully active, no load current flowing for predetermined time. So it goes into standby based on load activity. Not active, protected SMBus command. Don't know what that means. Oh, and the SMBus becomes active in ship mode. So maybe I don't understand what that means. Under voltage, not active. So we're definitely not in ship mode because I can measure voltage on the pack, on the outputs. So we're in standby mode. And as soon as we pull current, we'll be in active mode. So yeah, so if a cell goes under voltage, it's going to go into extreme cell under voltage mode, but pre-charge enabled. I wonder if that allows you to be mean to the pack and charge it somewhat to get it above that recovery threshold. So I mean, it looks like how I would have built a chip, if I had the brains to build a chip. 16 cells in series. Power LAN communication link. Patented serial network and protocol design for battery management. So fucking stupid. How about documented? I mean, fuck a patent. What else? Delta Sigma ADCs. See, yeah. Charge, discharge, and the rest. Whatever. Alright, that's cool. This is why you buy a chip, man. So you don't have to solve all these problems. Power pump cell balancing technology drastically increases the useful life. Yeah. Wank, wank. Efficiently transfers charge from cell to cell rather than simply bleeding off charging energy. See? You know, but let's patent that, because fucking nobody could think that up, even though that's exactly what I would do if I were designing something like this. Virtually no energy is lost as heat. Blah, blah, blah. Anyway, super cool. Okay, so here we go. So this isn't as impressive. Oh no, 10 milliamps to 1 amp. Yeah, so that is more impressive, because that's the thing, man. You want to be able to, especially when you're charging and you have a string that is a little bit higher, being able to transfer 1 amp. That's super useful, because bleeding off 1 amp, you know, at what, 3.6 volts, that's a lot. And I think typically most hobby chargers are bleeding off like 100 milliamps or 300 milliamps maybe. So anyway, that's not as ideal as parallel charging, but it is a very good compromise, and certainly is less wasteful. And then of course during the pack's runtime, it becomes a better situation. So anyway, yeah, these are going to be fun. I'm continuing to read because I want to see the SMBus stuff. I want to see what they say about it. So charge and pre-outputs are usually used in the MOSFET transistors to charge the cell stack. Charge pre-charge mode is selected based on the present cell voltage. So we're in one of those modes because I have voltage, which is sweet. It's disabled when a cell reaches a cutoff limit. We could short them and it would probably disable them until we remove the short. And somewhere in here is probably values of how long that should take and things like that. You can't disconnect this from the pack. It's welded, so I would expect it to remove the short protection as soon as the short is gone. Which is curious, because how does it end up detecting that? I don't know. If a cell voltage falls below programmable threshold or excessive current or other safety related fault is sensed, then it's disabled. So yeah, so I think once we figure out what these MOSFETs are, and there's 5 in parallel and two sets of those in series, which I don't understand, but we get the rated output of this pack, which I'm guessing, because it's 3 parallel connectors, I'm guessing it's the 26 amp, because I don't think you'd want to pull 110 amps through 3 little connectors like that. So if I had to guess, we're good to pull 30 amps out of this thing, or 26 amps out of this thing, before it'll begin to decide whether or not that's an overcurrent condition. Oh, here we go. So is this SMBus? Yeah. So, it's a 2-wire system. So maybe it's in that connector. Neat. There's a website. Neat. SB data. I don't know if that's what keeps the historical. Laptop computer. So this is a bunch of shit I didn't know about. I didn't know that this standard existed. So I may have to go read about that. So here we go. Interesting. These are reserved. Look at that. We should be able to get the manufacturer, device name, chemistry. It's manufacturer data. So maybe this will have, you know, serial numbers or whatever. It's interesting. So it seems like they don't really account for what all of the data is or what the types are, but whatever. I think we should just be able to read, read all these locations and get out stuff. Permanent fail status. Lifetime. Here we go. These are the values that we want. Why are these grayed out though? That's what I want. I want to know these things. So maybe I'll have to go read about the SMBus protocol. So here we go. Here's a reference schematic. I am not one of those dudes, but yeah, again, our MOSFETs are all, we have 2 sets of these. And 5 of them. Maybe that's these guys over here. Battery plus, pack plus, the ground. Fuse. And here's our flow. Is this what I'm looking at? Is it so it can do some sensing across this little dude? I don't know, man. This is yeah, this is a 3-cell application, I think. That's what what this reference is. Power pump circuit component values types will vary by application. Yeah. Does it mark what is power pump? Because I'm assuming this over here is the area next to the connector that I was looking at, and this over here is the area with the what are those things called? The little wraps of the things that were potted. I forget what this called. Like little transformers. Little. What else? All right, so that's a bomb. Here we go. One, two, three, four, five, six, seven, 8. Yeah, this shit makes me feel stupid. Oh, there's our LED stuff though. So we could see if those traces go anywhere. I didn't see any LEDs on this thing. But then again, my eyes are old. No, I don't see any LEDs on here. Plus there's no button. Although maybe they only come on in a certain mode. A 16 cell application. So this is zoomed out quite a bit. Yeah, I guess we've got a bank of 5 here and a bank of 5 here. I think so. It must have something to do with their ability to be able to measure and turn on this pre-charged shit. And what else? Yeah. It's a lot like programming. You don't always have to understand how it all works. Unless you're Dave. "13 to 16 cells, blah, 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 blah." Anyway, cool. So that's what this is. So I was right. So it's not bleeding. It's way more efficient. Yeah, next step, charge this fucker up. See what happens. Okay, I don't know why, but if I unplug my other USB camera, I got my little piece of shit thing working, which is really awful. So let's see if we can figure out what these chips are here. Oh, is that guy gonna be readable? It's hard to navigate. All right. I mean, I can't fucking read that. What's amazing is that, like, the human eye, like, I can see that there's letters from the angle I'm looking at it as, and they're quite clear. But you get up on there and oh, here we go. Tell you what you want to patent is something. This shit should be written with that paint that always, like reflector paint, like fucking, so that the incidental light gets reflected exactly back from where it came from, so you can always read this shit head on. So there's that. So let me go look these up. We'll see what they are. Yeah, so I think I may just end up throwing this on a 2 amp just car charger. I think I have one that roughly regulates at 2 amps. That should be fine. And it's not smart, so it's probably going to try to charge it up to, 15 volts or something. So the BMS should protect it. So I may go slap this on that charger here shortly while I'm fucking around in the shop. And shit, I didn't write down the chip. So we get to be all inception-y here. Wait a minute. I don't have him. Oh, that's the one where, yeah, that's super inception-y. Alright, what does that say? Oh, I didn't fade this over. Alright, so FBF98B? Maybe? That's me talking. Here we go. FBF98B. FBF98B. Dear Google. MOSFET? Eh? Oh. 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 I mean, I assume that's what those are. Did I read it wrong? Or is it a FDMC 6679AZ? That's a mouthful. 6679AZ. Oh. Oh. FDS 6679AZ. FDMC. Let's go to Palulu. I love those guys. I'm guessing that's what this is, just in a different package. Derp, derp, derp. What do we got? Dissipation. Pulsed 65 amps. Continuous 13 amps. These are in negative. I'm assuming that's because these are discharged. I don't know. That's weird. Negative amps. Somebody who's not a dummy can tell me why they measure them that way. Up to 20, yeah, plus or minus 25 volts. So 13 amps continuous times 5, right? So it may be that MOSFETs are over spec'd. And they do, they logically do the current limiting at 119 amps. Shit. I don't think I'd want to pull that much out of, let's see, 8. I mean, that's only 21 amps per cell, which these cells are totally comfortable doing. But that connector, I don't think I'd want to pull that many. So maybe the SMBus will tell us what the value what we've got that value set for. Yeah. Average pack current. Dude. At rate, time to full, not supported, huh? That'd be freaking cool. But it doesn't do any of that. Charging current, charging voltage, cycle count. Totally want to see that. Huh. Yeah, so I mean I guess maybe I don't understand the configurable operating currents. Obviously something measures that current, so I don't know. Is it this dude on the final output here that is measuring the current? I don't really know how anything works. I don't know how anything works. MCC S100 154. That's gonna be a fuse though, because I don't see it going anywhere. Yeah, I don't see it connected anywhere. Huh. Alright. I don't see that connected anywhere either. So I don't know, the current measurement might be on the underside of this board. I'm guessing the MOSFETs don't give you current measurement. So anyway, how that's programmable. Yeah, I'll have to maybe try to understand that or not, but certainly it seems like with the MOSFETs that are on here, what was our math? 169 continuous? That just seems crazy. Alright, cool. I'm really done this time. I'm gonna actually go throw these on the charger and go do some car stuff.